In this video, what we're going to do is have a look at the reactions of the acids anhydrides, and if you're using your college notes, we'll be looking at pages 7 and 8. So first of all, we need to make sure we fully understand what an acid anhydride is. So acid anhydrides, they're derived from carboxylic acids. So you can see here is that I've got two ethanoic acids and I have lost water. So I've removed this water. So we've got the anhydride, loss of water from two carboxylic acids, and we've got ethanoic anhydride here. So it's just to remind ourselves what an acid anhydride looks like. So the first reaction we're going to have a look at is the reaction with water. So in any reaction where water is used to break a bond, then we call that reaction hydrolysis. And when we hydrolyse acid anhydrides, we're basically putting back the water and we're going to form carboxylic acids. So you need to ask yourself, well, what's our reagent? Well, we're reacting them with water, so unsurprisingly the reagent is water. And then you need to try to write a general equation. Now I'm going to draw out my acid anhydride structure, I think it's easier to see, and then add the water. So if you have a look at what I've had to go at, you can see here, this is just a general acid anhydride, so I haven't specified which acid anhydride I'm using. I'm just using an R to represent any carbon chain. And what we're going to do is we are going to use water to break a bond. And what we're going to do here is that we're going to break this bond here, and then we're going to put the parts of water back on. So where we've broken this bond over here, you can see that I have put an O and a H from water onto this C, the first C in the chain, and then the remaining hydrogen has been left to add on to the other side, and we've formed two carboxylic acids. So what might be worth doing now is seeing if you could turn that into a structural formula. Could you write this equation in structural formula rather than drawing it out? Could you write it in structural formula? So you might just want to pause this video and then have a go at writing it out. So if you've had a go at writing it out, it should look like this. Now this here, RCO in brackets twice with then an O outside the bracket, is how we would write an acid anhydride in structural formula. We've got the R, the C and the O repeated on both sides. So if I see if I can find a highlighter, I've got the R, the C and the O repeated on both sides. I'm going to put that in the bracket here. And then the final O that's not repeated, that there's only one of, is coming outside of the bracket. Obviously water's just water. And we've made two identical carboxylic acids because these two R groups are identical, so we can just write 2RCOOH. So that's our reaction with water. And this is our acid anhydride and this is our carboxylic acid. Let's move on and have a look at the reaction with ammonia. When we react with ammonia, we're going to form amides. If you have forgotten what an amide is, it might be worth going back and having a look at the structure of amides at the front of carboxylic acids in our study packs. We're going to react with ammonia, so unsurprisingly again our reagent is just going to be ammonia. And I'm going to draw an acid anhydride out and I'm going to react it with ammonia. So here we go, we've got the acid anhydride structure with ammonia, and we're going to break again this bond here. It's like our bond, like an ester bond, but in our acid anhydride structure, and we're going to stick on N and two of the H's, because N can only have 3 bonds, so N and 2 of the H's, and then the remaining H is ending up on the other half. This half is getting the remaining H, and so we've got our amide structure here and a carboxylic acid. You will always get a carboxylic acid as a second product in the reactions of acid anhydrides. So again, pause the video and see if you can convert that into a structural formula. There you go, if you've had a go at that, you should have got something like this. Remember that this O is the one that's outside the bracket, and the rest of the structure that's repeated, the RCO part, has gone inside the bracket. We've got 2 of those. And we've got an amide and a carboxylic acid. So we move on and we'll have a look at the reactions of alcohols. We're going to form esters. So a bit more familiar with esters. So again, our alcohol is going to be our reagent, and our general equation is going to look something like this. So again, we're breaking this bond and we're sticking on the O and the R with a little dash to represent that it's different to these R's, and the H is going on to the other half. So again, have a go, see if you can write that in structural formula. So what we should have got, and we can see here that that's our structure of our ester as well as a carboxylic acid. Okay, so then we're going to move on and look at primary amines. Probably the most tricky of these reactions. Primary amines are going to react with acid anhydrides to form N-substituted amides. So our primary amine is going to be our reagent. And let's have a look at that general equation again. If we have a look at that general equation again, we're going to break this bond. We're actually going to use the lone pair. If you imagine there's a lone pair on this end, they're going to come in and attack and join on in a nucleophilic attack. They're going to add, and then we're going to eliminate the hydrogen in a second step so that we end up with one H and the R group, and the other H is going to go on this other half. So again, have a try at writing that in structural formula. So there you go. And we've got our N-substituted amide. That means that the name is going to go something like N-ethyl propanamide, depending on the length of things, N-methyl ethanamide, something like that, and a carboxylic acid. So let's have a look at the questions that were in the pack. You've got ethanoic, anhydride, and methanol. So the first thing you need to do is draw out those structures and see if you can work out what you would make. So pause the video, have a go, see if you can work out what you would make. So there you go, this is what I've come up with. I've got my ethanoic anhydride. I know that because I've got 1, 2, and it's repeated on the other side, 1, 2, ethanoic, and there's my methanol. Remember that I'm breaking this bond, and I'm going to stick on OCH3 onto this left hand side and just a H onto this right hand side, and I'm going to get these 2 products. Now you might have chosen to write your structures in structural formula, which you would look something like this. You might have even chosen to write in skeletal formula if you've done it in skeletal formula. If you haven't, maybe have a go, but if you have, it would look something like this. Can you name these 2 products? So what is the name for this and what is the name for this product on the right? Now the product on the right is a little bit easier. We've got 1, 2 carbons in a carboxylic acid. Remember, when naming carboxylic acids, always start from the Q carbon. So this is ethanoic acid. And when naming esters, again, we know that this is 2, so this is ethanoate, this is an ester, but what's on our ethanoate? We've got a methyl group, so methyl ethanoate. We've got methyl ethanoate and ethanoic acid. What about propanoic anhydride then, and ammonia? So have a go, pause the video, see if you can come up with the structures of propanoic anhydride, the structure of ammonia, put them together. This is what I came up with. So here's my propanoic, 1, 2, 3. Remember, I'm going to break this bond and stick on most of this except 1 hydrogen. So I'm going to get an NH2 here, and the hydrogen is going to go on this side. And we've got these 2 structures. So again, if you've done it like this, perhaps try it in structural formula, see if you can do it. Maybe try it in skeletal formula, see if you can do it. If you pause the video and have a little go on a piece of paper, you can come back and check whether you've got the structures right. So go in structural formula. We've got this propanoic here, anhydride and ammonia, and here we've got our structures of our 2 products. In skeletal, we've got our propanoic, 1, 2, 3, and our ammonia, 1, 2, 3, 1, 2, 3. What would we call these? So this is 1, 2, 3, propanamide. It's an amide, and this is 1,2,3 propanoic acid. So our next example, methanoic anhydride and water. So here we go, we've got methanoic just being 1. Now don't forget this H here. There's 1C, it does have to still have 4 bonds, so don't forget this H, and water. Again, we're going to break this bond, put part of our addition thing onto this side and the H onto this side, and we've got these two. In structural formula and in skeletal formula, let's have a look. HCO twice O. Skeletal is kind of odd looking and probably wouldn't be expected to do methanoic in skeletal. Skeletal's about saving time and methanoic isn't particularly big. So you aren't saving a lot of time by turning it into skeletal formula. What's the name of our product? It's a carboxylic acid. Again, from the skeletal formula, quite hard to name, but if you look at this, it's a 1-carbon carboxylic acid. It's called methanoic acid. So let's just have a look at this example. We've already got these two in structural formula, so it might be an idea to try writing this equation in structural formula first. Should have come up with something like this. Maybe you've tried to write it then in displayed or in some sort of semi-displayed where some parts are displayed, the functionality is displayed, but the alkyl chains are not displayed. That's quite a common way to do things. So here we go, I've not bothered to display my alkyl groups, but I have displayed the functional group. Or maybe you've done it in skeletal. Could you name these products now? We've got here one that's slightly more tricky to name because it's an N-substituted amide. So the amide functional group is this bit here. A bit hard to draw around, there we go. So this is the amide functional group. So the carbon of the amide functional group is here. That's number 1. And we're counting a carbon chain. So 1, 2, 3. That is propanamide. So that's an amide, propanamide. But what is this other part? So what is this other part? This other part here is an ethyl group. So we've got an ethyl group on a propanamide. We'd call this N-ethyl propanamide. N-ethyl propanamide. And then we've got propanoic acid. And then our last question is this mixed anhydride, so the two sides aren't identical and we're reacting it with propan 1-ol. So the first thing I would think about doing is drawing out the structure of propan 1-ol to make sure you know what that is, and then thinking of possible structures. So maybe the first thing I'll do is, what if I was to break the structure here and start sticking the propan 1-ol on? We'll maybe come up with these two structures. So if I break it there and stick propan 1-ol on, then I get this, and the H is left for this side, so I'll get that. What though if I were to break my structure on this side? What two products would I get then? So if I were to put the propan 1-ol here and just give this oxygen the H, then I'd get these two. Maybe pause the video now and see if you can name these 4 structures. So we've got these propyl ethanoate, this is propyl on an ethanoate and propanoic acid, and then here we've got ethanoic acid and a propyl, because it was propan 1-ol for both of these, propyl on a propanoate. Let's just have a look at the end here to explain why we would use acid anhydrides rather than using acyl chlorides. So all the reactions of acid anhydrides produce the same major product that the same reaction would of an acyl chloride. So why would we use an acid anhydride in preference to an acyl chloride? Well, we'd use an acid anhydride because they're cheaper than acyl chlorides. Make sure when you talk about this you do actually use that comparison. You don't just say it's cheap, because what's cheap? Acid anhydrides are cheaper than acyl chlorides. Acid anhydrides are less corrosive, so safer to handle than acyl chlorides. And acid anhydrides, when they react, they produce a carboxylic acid as the byproduct. When acyl chlorides do the same reaction, they always produce HCl as toxic HCl gas, not as hydrochloric acid. It's not in solution, it's coming off as toxic HCl gas. So that's very dangerous for the people working with it. They'd have to be working in a fume cupboard. So acid anhydride is just safer for that reason. Again, don't just say they're safer, you need to qualify that with a reason. So they're safer because they're less corrosive, they're safer because they don't produce toxic HCl gas, and acid anhydrides don't react with water as readily as acyl chlorides. Acyl chlorides, if you just literally take the lid off a bottle of acyl chloride, fumes of HCl gas will come out of that container as it reacts with the water in the air. Acid anhydrides, you will not get such a rapid reaction, and so they're a bit safer to use for that reason as well.